Howdy and welcome back. Let's go ahead and define our insertion behavior, which is going to satisfy the binary search tree property. So remember, the property of our binary search trees is that given some node x, if y resides on the left of x, it's going to be guaranteed that y's key value is going to be less than x's key value. Likewise, given some node x, if some node z resides on the right side of x, z's key value is going to be greater than or equal to that of x's. And notice here, as we begin to build up our tree, what if I wanted to insert, say, the value of 5? Well, there's one place where this could go that would go ahead and satisfy that constraint. We could go ahead and follow down, kind of walk down our tree beginning at the root until we find the correct location for 5 to be inserted, which is going to be right here. In this case, assuming we're inserting in order, notice that essentially what we're having here is it's almost a doubly linked list in some ways, minus the fact we have this right pointer, which is pointing to nowhere. But whenever we're inserting, when you get into 225, you're going to get into some ways to maybe, and this is probably not a valid rotation, I'm just showing you here very quick, something where you do like this to go ahead and rebalance the tree, and maybe, you take it a step further on the next insert or whatever. But if you notice here, I've rebalanced this into a height balanced tree. The right side is going to be of height 1. That of the left side will be 2. And in that case, it satisfies that height balanced tree where the difference in height between the nodes is at most 1. Cool? Okay. So again, we're not worrying about any sort of rotation. If we go ahead and insert, some nodes and our tree comes out like this, for today's topic or today's discussion, that's totally cool. We're not going to worry about doing any sort of rebalancing in this class, but you will in 225, and it's fun. It's a bit of a mind twist at first, but it's fun it's satisfying to see, this, this not appeasing structure to something that's a bit more friendly and has some more interesting properties. And if we were to look for, say, some sort of value, for instance, if we were going to look for 6 in that linear list, we'd be looking at 1, 2, 3 nodes. Whereas if we have something more tree-like, notice we're kind of getting there a lot faster. So let's go ahead and get into the actual insertion process here as we'll implement it for our binary search tree. Okay, so we have a function named insert. It's going to have 2 parameters, data, which is going to be of type T1, and key, which is going to be of type T2. I've gone ahead and decided that both of the arguments that are going to be passed to this function are going to be passed by reference to const. The reason being is that we'll see here, the first thing we're going to do is create a copy of those objects. Now, if you notice here, if we weren't passing by constant reference, a copy would occur to go ahead and initialize the parameters with the arguments. Instead, what we're simply going to do is bind the names of the parameters to the objects that are passed to our function, again, by reference to const. So first thing we're doing here, we're going to go ahead and create a new node with that data. Because we're inserting a new node somewhere into our tree, it's going to have to be at some location where there is an empty spot such that the insertion satisfies the binary search tree property. So here we are. We create a new node of type T1, T2. And remember that the construction of this node, and I'm only going to draw the key as well as the left and right pointers and the parent pointer. All pointers by our definition are initialized to the null pointer. And I'm, again, only going to show key here. Key is going to receive a copy of whatever is bound to our parameter key. And likewise, data is going to receive a copy of whatever has been assigned to our parameter data here. So at this point, we're going to be ready to go. We're going to have a brand new node all located on the free store. We're going to have the address to that node stored in our new node pointer to some sort of node object. Okay, we'll do this simple condition first. So we've got this brand new node, and let's go ahead and acknowledge the case of default construction of our binary search tree. If this is the case, remember that root simply points to nothing because we have an empty tree. If we get into our insertion procedure and we see that root is pointing to nothing, all we have to do is hook up our new node, so the address stored in there, and assign it to root. At that case, we go ahead and have root now pointing to this new node that we just constructed with some sort of data and key value, whatever that may be. Now let's consider the case, and notice here I didn't update any of the pointers because we've simply inserted a new node into an empty tree, meaning there's going to be at most one nodes within this tree. So the node's not going to have a parent because it is the root node, and it will not have any children because only one element has been inserted into it. Now here's where the fun begins, the process that we're going to see here. Let me go ahead and update this quick because this should be out a little bit more, and it might be a bit confusing if you're looking at this. Hold on. Okay, I just wanted to make it very clear that we'll see here the node, in the case that there's existing nodes already in our tree, we do have to update the new node's parent to point back to its parent. Let's go ahead and kind of look at this, and we'll go from there. Okay, so what's happening? Let's say we have a new node with the key value of, I don't know, 3 that we're going to go ahead and add into our tree. So remember that this thing started out with all of its pointers to the null pointer. Let's say it has 3. And we have new node pointing to that newly allocated object on the free store. So we have to find out where we can insert 3 into our binary search tree such that the binary search property is satisfied. And again, that means if we have some sort of node X, if Y is a node in the left subtree, its key will be less than that of X's. If that node is in the right subtree, its key is going to be greater than or equal to X's. So we need to find the position of insertion. I'm going to go ahead and have 2 pointers that are going to be involved in this process. One is going to be pointing to where we currently are in the tree, and then another is going to be pointing to the parent node of our current position. And we'll see the implications and why it's going to be maybe easier to think about using 1 pointer than it would be to do the process with 2. But let's go ahead and initialize iter to the root of the tree where this process is going to begin. And I'm going to go ahead and initialize parent to the same node. Now, the conditional that is going to get into this traversal process is going to be essentially while iter is not the null pointer, we're going to go ahead and execute the body of this loop. The first time around, we're going to assign parent to iter, and while they're both pointing to the same thing at the beginning, so the first time through, and they'll stay that way. Now we're going to go ahead and perform the movement. We're going to see if the key value, in this case 3, is less than iter's key. If it is, we're going to step left. Otherwise, we will step right. So in this case, 3 is less than 20. So we're going to go ahead and move iter from this node to point to that node. Now at this point, you might be going, why do we need a pointer to the parent? Because doesn't each node have a pointer to its parent in the list? Well, we'll see here momentarily. But we've just hit made the assignment of iter is equal to iter's left, and now we're going to go up and evaluate our conditional again. Iter is not pointing to the null pointer, so we're going to continue this process. Parent is going to equal iter, so parent gets moved, and then we need to make a decision. Is the key we're looking to insert less than that of the node we're currently on, or greater than? It is left, so iter is going to be moved to the left. So at this point, iter is pointing to the node with the value of 4. We come back up and evaluate our while statement's conditional. At this point, iter is still pointing to a valid node. it has a valid address, it's not null pointer. So we're going to go ahead and get into the body again. Notice at this point, parent is going to be moved down to point to this node. Now we're going to go ahead and look at the key 3 of the new node we're looking to insert and compare it against the key of the node we're currently on. In this case, the key that we're looking to insert is going to be less than that of 4. So we're going to go ahead and move iter to that node's, oops, there's my eraser, that node's left. Well, guess what that node's left is? It's the null pointer. So at this point, iter and parent's left will be pointing to the null pointer. So notice here, at this case, we're no longer going to continue this traversal process because the condition for our while statement is no longer satisfied. So we're done with it, and we're going to go ahead and jump to what comes after it. Now we see this interesting statement. It says if the key is less than the parent's key, parent's left is going to equal that new node. Otherwise, parent's right is going to equal to that node. Notice at this point, we've effectively isolated the place where we're going to insert, and now we just need to check once more to ensure it's getting tacked on into the correct child pointer of the parent node. In this case, parent's left is going to point to that new node. I guess we'll do that. So at this point, this node has been absorbed into the list. However, there's one last thing we have to go ahead and do, and that's to update the new node's parent to point to the node with the key of 4. And at this point, we can say, I'm going to go ahead and erase this, that 3 has been absorbed into our binary search tree, and it has been done so in a manner that satisfies the binary search tree property. So here's just, I don't know, I'm building this up. These are some cool little diagrams that if we go ahead and provide you with an activity on the binary search tree, you'll have access to. This is similar to my linked list printing. It took far more effort than maybe it was worth to go ahead and get this presented for you, but actually no, it's good because it'll help you visualize. So anyways, we start out with an empty binary search tree through default construction. It's identified by BST. We go ahead and run bst.insert Michael, my name, with a key value of 20. Notice here's kind of the data type. Here's the key type, and then our parameter constructor type. Here's our data. Here's our key. First time, if we were to print BST, default constructed, it's empty. If we go ahead and call insert the first time, we can see that a node with Michael is inserted at the root, and its left and right pointers store the null pointer. If we go ahead and insert Lauren with the key value of 8, we have to run through that, that process of isolating the correct location where this record should be inserted. Now, 8 is less than 20, and there's no left subtree of 20 in this case, so 8 will get tacked on there. And the right, there is no right subtree at this point, as communicated by the, so here's the root, key value 20, data's Michael, here's the node to its left, key value 8, data Lauren, right is the null pointer as communicated by here. And notice that Lauren's node has no left. It has no nodes on its left nor no nodes on its right. So let's go ahead and continue on. So we have Michael, Lauren, some null pointers on in the empty direction. So now we're looking to insert Bill. That's a key value of 4. So we're going to go ahead and step left again, and insert that record there. Now notice how the diagram on the right, it's just this kind of little ASCII tree. It's communicating the same thing. So up at the root, me, to the left of me, Lauren, to the left of Lauren, Bill, as shown with the indentation. Bill currently points to no children. Right of Lauren, there's no children. Right of Michael, there's no children. Let's go ahead and insert Alexis, 20. So let's set this up. We had 20, 8, 4, couple options, couple open spaces. Comparing against the root key, we see that okay. This key value that we're looking of the record we're looking to insert, it's greater than 20. Okay. We'll go ahead and step our iter right. We're at the null pointer, so we know we're going to tack on to its parent in the right direction. And we go ahead and insert that there. Alexis, left and right, has no children, just was inserted, and that's effectively communicated here. So hopefully that's kind of clear, the process. Again, it's just walking through the list and finding the location where we can tack on a new node. So we have to find some sort of pointer in the proper direction that will allow us to insert in a manner that respects or satisfies the binary search tree process. So we'll go ahead and get into the destruction process now to close out the lesson.